So, many of you, how many of you were at the thing I did last night, the public, at least half. So I'm going to skip, some of the stuff I'm just going to skip over quickly because I did it last night. But here's what I want to do. Here's the basic overview. I want to talk a little bit about what we know and don't know about climate change generally. All right, this is not necessarily it's just what we know and don't know. I want to talk about climate catastrophic outcomes because that's what matters. That's really all that matters. In fact, that's what I think generates the results that Simon showed us. I want to talk about fat tails. This is, this conference, what is the title of this thing? It's wow.
That's fat tails.
Yeah, this word has really been misused. Fat tails has very little to do with catastrophic outcomes. Fat tails refers to a distribution, a probability distribution that declines towards zero slower than exponentially. That's all it means. All right? Thin tails, it declines to zero faster than exponentially. You can have a thin-tailed probability distribution of, let's say, temperature and have a catastrophic outcome. And you can have a catastrophic outcome or serious probability of a catastrophic outcome with a thin-tailed distribution. So fat tails has, I'll go into this, I'll explain it, very little to do with what we're here talking about. Anyway, we'll go over that. I want to talk about, I'll do it really quickly on IAMs, but I want to talk about the alternative, which is surveys, which I've done. I want to show you the results. And then, of course, the big issue is climate is only one catastrophe. And down the street, they're looking at, nuclear terrorism, and in the other direction, they're worried about megaviruses and so on. So I want to talk about that. All right. So what we know and don't know. So first of all, we know that emissions accumulate in the atmosphere. I use CO2 to mean greenhouse gas in general. CO2 equivalent accumulates in the atmosphere, and that can eventually cause warming and do other bad things. All right, higher sea levels, things we don't like. And on net, they're bad. They will reduce GDP, broadly defined. I use GDP to include other things like morbidity, increase mortality. I'm going to monetize all that and put it in GDP terms. That's what I mean by it. And so that's going to reduce social welfare. It's bad. And that means there's a social cost of carbon. And you can think of, if you knew the social cost of carbon, that would tell you what to do. You'd have a carbon tax. And it's the basis of a carbon tax or equivalent policy, such as tradable permits. But what we don't know is how big the social cost of carbon is. And the estimates that are out there vary from, very small numbers to very large numbers, well over $200 a ton. Can we use integrated assessment models to figure this out? That's a growth industry, and as I've said many, many times, these models are not very useful. And what matters in terms of figuring out the social cost of carbon, the only thing that matters really is the chance of a catastrophic outcome. And that's the key, is what is the probability of that happening. All right, so I don't want to spend much time on this, on integrated assessment models. Basically, what goes on here is that there are two key things that we don't know much about. We don't know climate sensitivity. I'll tell you more why. Climate sensitivity tells us if there's a doubling of the atmospheric CO2 concentration, what will happen to temperature, mean temperature, once you get back into equilibrium? It takes about 40 or 50 years. How much will it increase? That's called climate sensitivity. We don't know much about it. We know a lot about the science, but we don't know the number. And when it comes to the damage function, we don't know anything. Absolutely zilch, nothing about damages. We have no idea what a 3-degree increase in temperature would do to welfare, to GDP, to morbidity, to mortality. We have no idea what a 5-degree increase in temperature would do. We just make stuff up in these models. And that's one of the reasons why the models are all over the place. And my biggest concern with these models, there are all kinds of bad models out there, but my concern is that they create a perception of knowledge, a scientific knowledge and precision. And that perception is totally, illusory and totally misleading. And that's what bothers me about these models. It's using, a big model on a computer, and it's complicated, and to make it look scientific. But it's not. We don't know anything. Okay. just a couple of things. Why don't we know climate sensitivity? Again, this is what it is after you get into equilibrium. The problem is the feedback loops. So we know a lot about the science, and we know that there are 4 or 5 critical feedback loops that determines the value of climate sensitivity. And we just don't know what the values are, the parameters of those feedback loops. That's the difficulty. And to see what's going on, let's just make this really simple and wrap up all those feedback loops into one feedback loop. And the feedback parameter is F. So suppose that S sub 0 is what climate sensitivity would be without any feedback, but it's the feedback loops that make it big. So F makes the climate sensitivity bigger. It's a number less than 1. The problem is that to get high climate sensitivity, you need an F that's close to 1. So is it 0.98? Is it 0.99? Well, if you think about it, 0.98 versus 0.99, that doubles climate sensitivity. So uncertainty over F leads to huge uncertainty over S. That's the difficulty. We just don't know what these parameters are. Worse than that, what's come out of climate science in the last 10 years is that our knowledge of this, our ability to tell what that is less than we thought 5 or 10 years ago. There's even more uncertainty now than there was 5 or 10 years ago. That's what we've learned. It's not that climate scientists aren't working hard and learning stuff. We're learning about our inability to predict or determine climate sensitivity. And it's because of the feedback loops. Okay, so that's the problem with that. And what about the damage function? Well, here's the Nordhaus dice model. That's what it is. And this is just made up. And the parameters are chosen to give numbers that were kind of consistent with the IPCC, that 3 degrees, 2 to 4 degrees gives you, maybe a 3% drop in GDP. Nordhaus referred to the IPCC for those numbers. The IPCC, where do they get the numbers? From their survey of IAMs. Kind of circular. So we just don't know what this is. It's totally made up. If you make this a random parameter, you make this, replace 2 squared with gamma, and then choose numbers for gamma. The problem is when you're choosing numbers for an exponent, you're going to get draws from the Monte Carlo that are going to lead to huge, huge losses. That's the difficulty. That's why I thought that was what was generating some of the results in your study.
Actually, that's not exactly how it is.
Okay, anyway, but whatever you... One thing people will do is run Monte Carlo simulations by varying these parameters. My point is simply that this is a made-up function, totally made up. There's no science, there's no theory, there's no empirics, there's no nothing behind it.
Just some clarification quickly. So alpha and beta are just random parameters.
They're not random. Nordhaus will pick numbers, but they're numbers.
They're numbers, but they don't have a meaning.
No, they have a meaning. I mean, the meaning is that if you pick these numbers correctly and you put a temperature in, this T is the increase in temperature from people resulting from human activity. If you put a number like 2 in here, you're going to get a loss of, this is going to be 0.98. You'll have a loss of 2% of GDP. Okay, so that's how you pick those numbers.
So they're calibrated by the function, the end result that you get out of it.
Yeah, for the end result you want. You pick these numbers to get the result you want. Got it? Yeah. What you want. That's how you pick the numbers. That's how you pick the function. That's how you pick the whole model, to get numbers you want. So you can put anything you want in here. Am I being a little tough on these models? Anyway, look, it's not that we could do better. We just don't have any experience. We have no data. We have no experience with this. We can go back. People say we go back 100,000 years or 1,000,000 years, and we see that then there were big temperature changes. But we didn't have a modern economy 100,000 years ago. London looked different back then. So I think. So I'm told. So we don't have any experience, and we don't have any theory. Nothing. And the real problem is adaptation, because when things change, we adapt. We plant new seeds, we generate new kinds of grains. That's what happened when people moved west. They started out in the United States, they came from here. and they came to the eastern part of the United States. They dug in the ground to plant stuff. It's terrible. You dig in the ground, it's all rocks. And then they went west, and they got to Iowa, what's now Iowa, Kansas, so on, and you dig in the ground, and it's just wonderful, rich soil, no rocks. The only problem is it's much, much hotter in the summer in Kansas than it is on the East Coast, and much colder in the winter, and the grains that they were growing on the east, corn, for example, wouldn't grow in the middle of the country. So what did they do? That's how we got hybrid corn. You develop new strains, you adapt to the difference in temperature. Okay, so we have no knowledge, we don't know what's occurring, we don't know how much adaptation there will be. People argue about this. There could be quite a bit of adaptation, could be difficult to adapt. All right. I'm going to leave the discount rate now because I think you've heard enough about it, so I'm going to leave it completely. You're right, we don't agree on the discount rate. I will say that if you take a model that isn't, if you don't have random variation in some of these parameters, the discount rate will matter. You can get very, very big differences in the SCC from different discount rates. All right, but I'm not going to dwell on the discount rate right now. So what about catastrophic outcomes? Why is it that they're so important? So the U.S. Interagency Working Group, this is a government body in the United States that had to come up with a social cost of carbon because in the United States, federal agencies and state agencies issue regulations, and they are required by law in some states and by the federal government to use a social cost of carbon. And so they need a number for it. So what they did, this group, took 3 models and 3 IAMs, and they ran them, thousands of times, and used a 3% discount rate, which they agreed on because they wanted to go home. I mean, that's really how they agreed on it. Enough's enough. We're going home. 3%. That's literally what happened. And they got 3%, and they took these 3 models, and it's amazing. And they got the latest estimate of the social cost of carbon is $39. Just to put that in perspective, that's a small number. So with that number, you don't have to do very much. You're not going to change your lifestyle very much. Okay, that's a pretty small number. So, but anyway, that's what they got, and that's what we're now using in the United States. And actually, most of the numbers that are thrown around, like in the Paris negotiations, they don't have a social cost of carbon, but are sort of similar to this level of a social cost of carbon. All right, but what happens is these things are based on kind of most likely scenarios, and the question is, what happens if we think about a catastrophic outcome? What if we think that there's a reasonable probability, 5%, 10%, 15% probability that in 50 years or 60 years, we're going to have a catastrophic outcome? And what I mean by catastrophic is a drop in GDP relative to what it would have been otherwise of, let's say, 20% or greater. Okay, 20, 40% drop. And I'm doing this in terms of GDP because I'm an economist and because we need something. If we're going to get, a social cost is measured in dollars or British pounds or euros. So we need something that converts things into those numbers. So again, we're using GDP broadly defined, but if we think of a catastrophe as something of a 20% or greater drop, we can get much bigger numbers for the social cost of carbon, as I'll show you. By the way, during the Great Depression, GDP dropped about 25%. It was about 25% lower than where it had been in the United States for about 8 or 9 years. At the end of World War II, Japan's GDP was about 70% lower than it was at the beginning of the war. Just to give you a sense of what those numbers might mean. Okay. Again, you'll get a much higher, you could get a higher number for the social cost of carbon. The issue is, how likely is such a scenario and how bad? What's the chance of a 20% drop in GDP in 50 years? Or even a bigger drop, 50% drop in GDP? The models can tell us nothing. Yeah?
Just to clarify, where do you get these statistics for the Great Depression in Japan after the war?
Where did I get the numbers?
You mean GDP in the narrow sense?
Yes,
Not
I'm
in
sorry,
the
good
broad
point.
sense that you define.
Yeah, good point. That's absolutely correct. So in Japan, we're not including death. We're including their GDP, their economic production. Good point. So when you include more broad GDP loss, more broadly defined, it was much bigger. That's absolutely correct. Okay, so the models can tell us nothing. And I had an argument once, well, let me leave out who it was, but a modeler who said, oh, no, the model's got catastrophic outcomes. Because what he did is he put in a, where's here. He put in the damage function, this is what he had. He had a damage function, the loss function, so it starts at 1, and he had a loss function that looks like this, and then boom, there's a tipping point. And I said, well, where'd you get this is temperature. And I said, well, where'd you get this tipping point? I said, well, that's made up. So sure, the model has catastrophic outcomes. You make it up. So I don't think the models can be useful for this. Now, the problem, and by the way, the fact that there's a lot of uncertainty, I want to make one thing clear because some of you already, calling me a climate denier and all of that. The fact that there's uncertainty doesn't mean we shouldn't do anything. Quite the contrary, it means that we have to think about a carbon tax as an insurance policy. So it doesn't mean we don't do anything. The issue is how big a tax, how big an insurance policy do we want? So just before I get to fat tails, people say to me, look, you've been dumping on these IAMs now and talking about how bad they are. What should we do instead? So I felt I had to come up with something, and I'll show you in a moment what I did instead to come up with some numbers. But I want to say a little bit about fat tails. And this got in here because of the title of this conference. So this came, I assume, from Marty Weitzman's dismal theorem. So let's be clear about what that is. So it has two parts. Suppose we think that we're going to look at temperature, increase in temperature. And suppose we think that it's normally distributed. Okay, that's a thin tail distribution. The upper tail both tails go to 0 more rapidly than exponentially. Okay? But suppose we don't know, this is how Marty got at it, we don't know the variance, so we estimate it with Bayesian updating. Then the posterior distribution is fat-tailed. All right, it means it goes to 0 more slowly than exponentially. Now there are many other ways to get a fat-tailed distribution. One of the nicest is the Rowe-Baker. How many of you have seen Rowe and Baker? And yeah, the Rowe-Baker paper was a famous paper, and I strongly recommend it. It's about climate sensitivity and why we don't know what it is and why it's so hard to predict. But they have a distribution. Now that's partly made up too, but their distribution is fat-tailed, and they used it in the interagency working group. And it comes out partly out of the physics of climate sensitivity. So you don't need to go through this thing that Marty did to get fat tails. I mean, it's very easy to write down a fat tail distribution. That's the part 1. So who cares about fat tails? Well, we get to part 2. Suppose that temperature reduces consumption, something like this, and there's a constant relative risk aversion utility function, kind of like that. And you ask, this means that very high temperatures are going to give you a very low consumption and a very high marginal utility of consumption. And what that means is that expected marginal utility is unbounded. Expected marginal utility from a little bit of increase in temperature is unbounded. And what that means is that the expected gain from reducing temperature is unbounded. And it means that society should be willing to sacrifice 100% of GDP in order to limit warming. Now, 100% of GDP is a lot of GDP. I mean, that's a big deal. But we would do that. We'd eat leaves and grass and whatever. We'll do that. That's what this says. That's the dismal theorem. Now, the issue is how relevant is this? So first of all, let me just clarify and make sure you're clear on what's a fat-tailed versus thin-tailed distribution. So here's a thin-tailed distribution. It's an exponential distribution. It goes to 0 more rapidly than exponentially. This is the Pareto distribution. The Pareto distribution is fat-tailed. Well, it's fat-tailed depending on the value of alpha. And it's used a lot in representing catastrophic events. When you look at, for example, hurricanes, storms, they use this distribution a lot. So The mean of the exponential is 1 over lambda. The mean of the Pareto is this. If alpha is greater than 1, it doesn't have a mean if alpha is less than 1. The larger is alpha, the thinner is the fat tail on this distribution. And alpha less than 1 means it's obese. And then, there's no mean. The mean goes away. So I did something here. I should have made the means the same, but for some reason I didn't. I set these parameters so that the mean of the exponential is 2 degrees, and the mean of the Pareto is 3 degrees. So this is temperature at some point in the future. Temperature increase, all right? And look at what these probabilities are. The exponential, you see, 3.361, it gets 4.5 degrees, about 10%, and then it really drops off. And you can see it drops off very rapidly towards 0. Clear? The Pareto distribution also drops off, but not as fast. And when you get to 10 degrees, you've got a 4% probability. When you get to 15 degrees, there's a 2% or 2.5% probability. But now think a little bit about this. Is it relevant to go to 30 degrees, 40 degrees? That's what you have to do. To get this dismal theorem result, you have to go to 30 degrees, 40 degrees, 100 degrees, 200 degrees. Don't you think things kind of stop after 15 degrees? I mean, it's going to be really warm. So there's not much meaning to go to temperature increase of 30, 50, 60 degrees. That doesn't mean much. And what does it mean to talk about a utility of 0 consumption? Well, that's infinite. Marginal utility is infinite. Now, that's a large number. But we have to ask, if your consumption goes to 0, marginal utility is going to be very big. You'll be very hungry, all right? And you might die. But that's not infinite. See, there's a difference between very large and infinite. So if we put an upper limit on the utility function so that it remains finite as consumption goes to 0, there is no more part 2 of the theorem. And how much would society spend to limit warming? Well, that depends on where you put the upper limit on marginal utility and what the upper limit is. And, it brings us back to the meaning and likelihood of a catastrophic climate outcome. So, a catastrophic, and I talked about this in detail in a recent paper. So, a catastrophic climate outcome, you have to look at the outcome in terms of what it does to us, GDP drop. It's not necessarily a very large increase in temperature. It might be a moderate increase in temperature, maybe 5 degrees, but it may be maybe our economy will be very, very sensitive to that, and it might be a big impact of temperature on GDP. Or maybe temperature doesn't have that big an impact, but it will be a very big temperature increase. Those could be catastrophic outcomes. What we care about is an outcome, GDP loss, that's catastrophic. And it really has nothing to do with fat tails. We don't need a fat tail distribution. I'll show you in a moment, you can take a gamma distribution, exponential distribution, a thin tail distribution, and get a much more catastrophic picture than you would with a fat tail distribution. All right, so fat tails, forget about it. Next. Now here's the upper limit on marginal utility. Let's suppose when you get to 15 degrees, marginal utility jumps because we all die, and then it stays level. Okay? That would get rid of the result of infinite marginal utility, expected marginal utility. Gets rid of that result. All right, so I hope I've clarified this issue of fat tails and thin tails. All right, climate catastrophe. How do we estimate the social cost of carbon? What do we do? What's the alternative since we don't have models? My view is that at this point, the best we can do, I think, is kind of what we did in the United States during the Cold War, when the biggest catastrophe that people worried about was a thermonuclear exchange with the Soviet Union. What is the probability? What would happen? How many people would die? What would it do to the economy? You couldn't build a model. I mean, there's no point in trying to build an IAM about thermonuclear war. We knew nothing. We never had a thermonuclear war, fortunately. And so we used the Defense Department, RAND Corporation ran studies where they looked at, what are plausible outcomes? What's plausible? Plausible means that people say, gee, that's reasonable. And what are plausible probabilities? And I think that's all you can really do here. And you use expert opinion and try to get a sense of what do people think are plausible numbers for the probabilities and magnitudes of catastrophic outcomes. Forget about the middle of the road outcomes. They don't matter. You know, a 2% drop in GDP, a 5% drop in GDP, it just doesn't matter. It's not going to give you a social cost of carbon. I mean, it'll give you a social cost of carbon, but it'll be very small. It won't matter. So if you're really concerned about serious emission abatement, you have to look at the possibility of a catastrophic outcome. And I've lost track of time. When did I start? When do I end? Where am I?
We started around 10 minutes late, so you still have 5 to 10 minutes or so, but you can take a bit more.
Okay. Whoa. Okay, so I did a survey. And there's a working paper I'm just finishing. It's going to go on my website in a week, I hope. And I surveyed about 1,000 people. I got about 500-600 complete responses. I'm sorry, I surveyed about 6,000, but I got 1,000 responses, of which 500 or 600 were complete. I'm not going to go through. If we have time later, I'll tell you the details of how I picked these people. It's based on highly cited publications in the last 10 years. That's how it was done completely objectively. I didn't go and say, this is an expert, this is not. I just based it on citations in the climate science area. And it includes economists, climate scientists. I'll show you some of the results. The basic questions, and I got an average social cost of carbon, not what happens from a 1-ton increase today only. That's the marginal SCC. It's an average social cost of carbon, which is over the next 50 years, what is the benefit of trimming the tail of the distribution, getting rid of outcomes of a 20% drop in GDP or greater. And what would be the emission reduction needed to do that? The benefit, the savings of GDP from trimming the distribution divided by the total emission reduction is an average social cost of carbon. And that's what I calculated. And I did it for every respondent individually because I asked them, what do you think is the probability of a 2% or greater impact in 50 years? 5% or greater, 10% or greater, 20, 50, and so on. And I looked at their individual responses as well as took all of them together and fitted distributions. All right, so this will go up on the website soon. Here are some individual results, just interesting. First of all, a lot of dispersion. Economists are less worried about this than climate scientists.
Per ton of CO2 or per ton of carbon?
Oh, this is per ton of CO2, I'm sorry. This is per ton of CO2. So economists, but these are big numbers. This is $170 and $300. These are huge numbers. I thought there'd be a difference between North America and Europe, but there isn't. They're almost identical. This is everybody, all the respondents. And the key here is that they're all over the place. There's just huge, huge variation. When you go to people, now you can argue maybe I didn't evaluate expertise properly, but what you get when you go to people is huge variation in their views about the likelihood of bad outcomes. Here, what I did is I took all the responses. I did this also for different groups, economists, climate scientists, North America, so on. But this is for everybody, and I fit distributions. And this distribution here is Pareto. And the Pareto distribution, as estimated, had a huge value of alpha, so it ended up being incredibly thin-tailed. It's a fat-tailed distribution. But the estimated values of the parameters give you almost no damage. Gives you a social cost of carbon of maybe $5. But it also has a very poor fit to the data. These other distributions, well, one of them is generalized extreme value type 2, Frechet distribution. That's fat-tailed. The other one is a gamma distribution, that's thin-tailed, and then log normal, which is in between fat and thin, it's right on the border. So we have these distributions, which interestingly, this is a transformed number here, but this means roughly a 20% drop in GDP. It says that the probability of that is, this is 1 minus the cumulative distribution. Probability is 1 minus 0.74, it's about 26%. So that for those 3 distributions, taking everybody that was surveyed, we get an average probability, okay, of about 26% of an outcome that looks really bad, and we get, I didn't draw, here there's some, they differ somewhat, but even here it's a pretty sizable probability. The other thing to note is this, look at the dispersion, huge dispersion. So the higher up you are, the lower is the outcome you're expecting. These people think that a catastrophic outcome is extremely likely. And that raises the question of what do you do with this? And one thing you can do with this is argue, gee, people on average think that take everybody on average, you're going to get a really high social cost of carbon. You might ask, well, let's only take people who said they were confident in their answers and maybe trim the outliers. If you do that, you can get a social cost of carbon that drops down to about $80. Still much higher than the numbers that are used in the US government. Okay. Now do I have at least 5 minutes or something?
Take 5 minutes.
All right, so I'm not going to spend any more time on the survey. Look, here's the complication. Complication is that once you're in the world of catastrophes, let's talk about catastrophes. There are other catastrophes we have to worry about that are perhaps much more likely and could happen much sooner than a climate catastrophe. A climate catastrophe, most of us will probably be dead. I don't want to upset you, but anyway, we're looking 50, 60 years in the future, right? So we're looking in the far future. If you think about a megavirus, if you talk to people, virologists, epidemiologists, and ask what is the likelihood of a really bad virus transmitted from animals to humans, all right, through mutations, that would have a devastating impact that could kill 10% or 20% of the world's population, they will say that it's quite likely in the next 20 years. Remember, the Spanish flu of 1918 killed 5% of the population of Europe and the United States. It killed people in other countries, we just don't know the numbers. But in Europe and the United States, 5% died from the Spanish flu. And we didn't run around on airplanes and trains and crowded buses back then. So we hardly had cars. So nowadays, something like that would spread much more rapidly and could be much more virulent. So the epidemiologists will tell you, look, what are you guys worried about climate for? We're not going to be around, 50 years from now. I mean, there are going to be many fewer of us. And then you talk to the people at the Kennedy School who do nuclear terrorism, Graham Allison and his group, and they will tell you, what are you worried about climate for? In the next 10 or 20 years, almost for sure, we're going to have nuclear terrorist events that occur in which Hiroshima bombs with the power of the Hiroshima bombs are set off in 2, 3, 4 US or European cities. Very easy. If you get the material, if you get enriched uranium, it's extremely easy to build a bomb. Very, very easy. It'll fit in a lead-lined suitcase. You bring it into the United States on the West Coast. They don't check anything that comes in the West Coast on all those shipping containers. Really easy to bring it into the U.S. So don't bring it to the U.S. If you look at this, read his book on nuclear terrorism, it'll keep you up for a night or two. And, that's a big deal. And we don't do anything. We're not doing much about that. Extreme, not just nuclear terrorism, nuclear war, bioterrorism. Some people say when I raise nuclear terrorism, they say, sure, 3 cities, 3 million people will die, but then it'll be over and we'll be back to normal. We will never get back to normal at that point. Life as we know it will change enormously once that happens. You look at what happens in the airport where you have to take the toothpaste out of your bag. Just imagine what would happen after nuclear terrorist attacks. Extreme earthquakes, extreme volcanic eruptions, unlike things we've seen in our lifetimes. So, you can go on and on. We can go on and on with these things. But these are real things. And, one question is, can you treat them individually? So I, together with Ian Martin here at LSE, have been doing some work trying to show that these are actually all interconnected. You can't, we're in the climate business, they're in the epidemiology business, they're in the nuclear terrorism business. Let's just all mind our own business. You can't. It turns out these things are all interdependent. And the reason is they're not marginal. They're not marginal. They affect the overall economy in a big way, and that interconnects all of them. They're all interconnected. And that's one thing. And the second thing is, as I look at it, you know, I think climate is a real issue, but wow, I think that viruses are a bigger issue, and nuclear terrorism is probably a bigger issue. And I see that we're doing almost nothing about viruses. The Centers for Disease Control in the United States, the World Health Organization in Europe, their budgets have shrunk in real terms, keep shrinking. We're basically doing almost nothing. And again, you want to bring a nuclear device, or you want to bring shoulder-fired missiles into the United States, just go via the West Coast, shipping containers, it's easy. So, on that happy note, I'll stop.